So I'm Cliff Click. I guess I was known for a long time for working on Hotspot JVM, doing all sorts of interesting stuff with Java. For the last year, I've been working on writing Java instead of implementing Java, which is sort of a different thing. Turns out the tools for writing in Java, if they're not Eclipse, are typically more primitive than, I don't know. So I'm enjoying my Emacs and Java experience. It's very different. So what I've actually been doing is trying to write a system for doing distributed computing. So all the talks that were done earlier on data parallel Java and data parallel this and that are sort of being, it was like taking a page out of my book here, is exactly what I'm going to talk about today, is how to do something interesting on a Mac. No, here we go. How to do something interesting with a whole lot of computers and a whole lot of data. So what we've got is an open source product, an open source company, hexdata.com, so hexadata like hexadecimal, and there's a GitHub, you can go download and play, and it's a platform for doing math, so parallel distributed math of all kinds. In particular, we're focused on machine learning algorithms, but it's actually like a giant vector calculator for vectors that are larger than fit on one machine. And you can program it with REST and JSON for people like doing NumPy and scikit, R, that kind of stuff, but you can also get under the hood and program it in Java, and below that layer there's a key value store that happens to be actually really high performance. It's basically a hash table lookup on any key value put or get, although it follows the full Java memory model semantics, so it has like exact precise semantics. It's not lazy or anything. And we do distributed fork join, and we do MapReduce and a KV store, and the combination gives us a system that's actually pretty convenient for doing lots of interesting kinds of math. Okay, so this talk is going to be about what I'm doing with distribution of data. So people talked about moving code to data and data to code and having it in the right place at the right time. I'm not doing anything with GPUs, so this is about doing it in the Java heap. But in particular, I'm going to talk about looking at a big vector. So when I say a big vector, I mean something that's got more than 2 billion elements, right? More than an int's worth of values. So the length has to be a long. It's not a Java int anymore. I still have to have fast random access, because if I don't have fast, it's big. Now it's really slow. And it's got to be random access just for convenience. So there's definitely a coding style or a pattern which will give me Fortran level speeds. But I can do random access pretty quickly as well. I'm going to support missing elements, which is a value that's somehow outside the domain of the number space I'm looking at, saying that this element is missing, and that's because this is a concept that's very important. I think Jan Vitek mentioned this for R. The machine learning statistical community finds it very important to have the concept of missing data. And then, of course, they're writable and variant in size and all kinds of the useful things you imagine out of a giant array. So when I'm looking at this thing, I have this taxonomy of data, a single big vector here. I'm going to short call it a vec. It's very large. And the contents, this is more than 2 billion elements, so the length is big. The contents are some kind of Java primitive, usually a double, but I'm not going to tell you what it is, and you don't care. As long as I can return you the bits that you gave me back later, I'm going to hand you back exactly those bits. But I'm going to compress furiously. My compression ratio is often equal to gzip. Sometimes it's 2 or 4x better than gzip, so it's quite compressed in memory, and yet I'm going to be able to pull it out at sort of line wire speeds, memory bus speeds, and do math on it. And then I'm going to support random access in there somehow. But if you're doing stride 1 linear access walking forward, I'm going to still be like memory bus speed limited despite my decompression on the fly. And so basically, it's Fortran speed on compressed data. That's the kind of fun stuff going on there. So I say distributed, so that actually means the data is on different JVMs. And here I show, for instance, 4 different JVMs, each with 32 gig heaps. And I've just sprayed the data across them. I am keeping my data in heap instead of off heap. That gives me really nice Java access to the data, and it's really fast in that sense. But it means I have GC issues. But it turns out that because my data is in large byte arrays, that GCs very cheaply, so I get full GC times that are typically 1 to 2 seconds, even for 32 or 64 gig machines. So that's fast enough that for the bulk math kinds of things I'm doing, I don't care. I do watch in my full GC cycles when the amount of data I'm caching exceeds what can usefully be kept in the Java heap, and I'll spill to disk. So basically, I have the whole Java memory beans things, you did enough allocations of giant gigabytes and gigabytes and gigabytes, and eventually you ran out of space, and I'm spilling the disk and loading it back and forth as it goes. As long as you have some kind of locality in your data access pattern, you won't ever see the spill to disk. But this is the backup plan for when you decide you want to play with more data than will actually fit in some of your heaps across your cluster. So when people talk about data in sort of the real world direction to do something, it's not just one of these big vectors, it's a pile of them. And so now I have a data placement issue where I want to know that the data that's in this piece and this and this and this are all co-located on the same machine. So this is the, where did the data land? So I'm definitely doing data motion to force all my data bits to align within the JVM so that if I walk across any row, it's going to be as fast as I can get it in and out of memory. Furthermore, it's also data parallel. I guess John Rose touched on that a lot. The actual access patterns people are doing here are typically very data parallel. Oh, okay, so yeah, back to this one for a second here. The collection of things that somebody works on is actually very similar to an R data frame. It's just this whatever giant collection of vectors you're going to have. And people will add and remove vectors where a vector describes some real world piece of data. I gave some examples here. It's sort of a struct of arrays notion instead of array of structs. Column counts on data sets I look at typically vary between 10 and 1,000, although we'll do get people who look at column counts on the order of tens of thousands. And then there are the sparse folks who like millions of columns.
Oh, I was just going to ask, is this sparse vector? Does it matter if I start at current time millis or not?
I'm not sure what the current time millis one is.
I just mean that's a big ass long. That'd be like, let's say I'm just using it for time series data and I want to use.
So I compress furiously. So if you hand me stuff like current time milling numbers one after another, it's a very common scenario. I'll do base and offset, delta encoding. And so that kind of compresses pretty furiously. So okay, so the column counts, I'm good up to say 10,000 columns at the current set of math algorithms. So the math algorithms care if you have millions versus however many columns, right? So a lot of the math algorithms we've implemented so far are all headed for dense. So few columns, long and skinny data, right?
Can I index anywhere into that vector?
Yeah.
And if it's empty before that, does it use up space? Is it slow? Is
No, no.
Okay. That's some about this.
So yeah, okay, well, let's go on here. Hang on, we'll get more into this. So I have chunked my data internally, where a chunk is typically 1,000 to 1,000,000 elements, but under compression, maybe it's more. And they're stored in compressed byte arrays scattered throughout. And I've arranged the compression strategies as just a few clock cycles pulling it out to do something. And usually what it really means is that for each chunk, there's a custom compression scheme built into the header on the chunk. And I pull a byte out, and I shift scale at it, and that's the double that you gave me in the first place. Right? Now, if the compression scheme says it's bit vector encoding because it's Booleans, then I do a bit shift mask crap thing. And if it's run length encoding, there's some other games going on. So there's something under the hood here to decompress, but I'll totally take the compression scheme. So it's generally a handful of clock cycles if you're going stride one axis through the data. And that's typically less time than even a streaming prefetching cache missing x86 will feed when I'm doing the dense algebra going down the line, right? So I'm bandwidth bound, and so this is entirely hit by the cost of memory. So I'm looking at data sets that are much larger than my caches, but small enough to fit in memory. Because of my alignment games, I can walk across a row at sort of the same speed. Everyone's prefetching in parallel by the x86 hardware games, and so as long as I'm talking about things like that in parallel, it turns out that it behaves like a Java object that's got a struct with a variable set of fields, if you will. The speed is still full speed. And I can read and write in that way, although if I have conflicting writes, I'm going to obey the Java memory model rules, which in this case will say, I'm not doing any synchronization here, and I'm not going to let you do synchronization at that granularity. So the answer will be you'll get sort of the last writer by potluck. But we can go into details of what that really means. So what really happens here is instead of running arbitrary Java code, I'm going to run a subset of Java code that I can make run fast and make easy enough to code to you can do interesting stuff. And that's exactly what we're going to hit into here, okay, in just a second. So speed-wise, okay, so given that this is a chunk of 1,000 to 1,000,000 elements or so, typically a CPU will work on a chunk of rows going across, and that's big enough that I can cover my control overheads for launching threads and killing threads and so on. And I'm actually doing fork joins, so I can probably get smaller than that, but it's definitely big enough to cover any fork join overheads. But I still get really good fine-grained parallelism out of it. And this coding style, MapReduce maps very well to a whole lot of interesting things that you can do with this stuff. So I'll get into that in some point down here. But it's not that I'm limited to MapReduce, it's just it happens to be the common case scenario for writing most of my algorithms in. And then we do the obvious thing. Everything runs in parallel on all machines. They all grab their chunks, they all run in parallel, fork join or load balance within a JVM, and I'll move code or data across to load balance across JVMs. Mostly, though, I move code to my data and run the data in place. Fork join and MapReduce are handling all the synchronization rules within chunks, and my H2O system is handling the communication across the JVMs, the clustering and the load balancing. So to summarize, a frame is a collection of vectors where each vector is some interesting real-world thing like age of a person. The vectors are internally broken up into collections of chunks. The chunks about 1,000 to 1,000,000 elements, and elements conceptually a Java double, although actually what it's compressed to is whatever it's going to compress to. And then the typical use case is that people are doing sort of stride one axis, walking across row at a time across this collection of vectors. Okay, so let me switch states to distributed coding taxonomy. This one's a little simpler. I can treat the thing as a black box where I have whole algorithms or whole vector math, in which case you're not doing any distributed coding yourself. You're just saying add vector 1 to vector 2 and get vector 3 as a result. Or you're saying run me a logistic regression or k-means or whatever it's going to be. This is the rest in JSON where you just say poke it, load this data, run a generalized linear model, get some results out. But if we go under the hood, there's definitely a collection of desktop users who use this thing in this mode. This is you downloaded it from the Git and you plugged it on your desktop and you hit go and you start doing logistic regression. We definitely have a lot of people doing this game. But this talks about going a little further in here. And this is what can I do in a simple data parallel coding style? What can I talk about in a coding style? And most of it's going to be MapReduce. And then it's not the only thing I can do here, but it's the common case because it covers so much ground. And then I have some other interesting use cases. Because the data is actually kept in a KV store, I can talk about it as a value has keys, which is basically distributed pointers. Basically, I can have a graph. And I can do graph algorithms straight on the platform as well. Okay, so here's some simple data parallel coding. So here is a MapReduce, which is stateless. And I'm going to do an example from linear regression. I want the sum of squares. And so I say new MR task, and I have a map and a reduce. And the map is mapping from an input value to a result, in which case the result's also double. And reduce takes two things from maps or reduces and produces one in a pairwise thing. And this code will run right now as written on the systems. You can download and play with it right here. And this will distribute across your cluster and parallelize and run at basically Fortran speeds. It's going to be as fast as the hardware can feed the data in through the CPUs. So that's kind of I feel good about that one. So I started with this, and then we can extend some more here. So I can say, can I do something with state? And I'm going to talk more about state as we go here. Here's one where I'm saying, well, actually, linear regression first pass wants a sum of x, sum of y squared. And I can do this game where I've got local variables, some x, some y squared. And I'm going to add all three in the map, but then the reduce has to take care of it all. So what I'm doing here in this coding style is saying, yes, you can do something once per row, but you also have to tell me how to combine the results from multiple rows. And this is the thing that the compiler is not going to figure out for you. It's going to make this go fast individually, But the distinction of how you do the combining of things versus what you do on a row-by-row basis is something you have to tell me how to do that. And what, of course, I'm actually doing is I'm doing a batch at a time. So there's really a chunk getting passed in, and I'm doing for I equals 0 to some chunk length, grab something, and the at call is essentially like an array lookup, except it's doing decompression. And then you do the math. And this is the actual loop that's running. And if you use the prior styles, then I put the loop in there for you. Right, but you still have to write the reduce. Does that make sense? And the interesting thing about doing it with a for loop that's exposed like that is that you can do your own loop invariant games if you know something about your computation, that you have something you want to do once or not so frequently as every row, you can pull it out of the loop.
Does this ever move between your cluster members?
They do. Trying to think of a good way to point to this. Just bring it up now. OK, so it's a KV store with full Java memory model semantics, but also caching everywhere. So if you're not writing to the data, you can freely talk about any row at any point. And if it's a cache miss, it'll get hauled in locally, and you'll use it there. And that will remain in place until somebody writes to it, and then it gets evicted out of the cache. Right? So in the occasional use, this is fine. If you're doing it every time, then you end up hauling all the data into the one node, and he's going to drown in the data. Right? So it's going to be too much. So the coding style for which that works, there's a limited set of coding styles. One of them is any sort of mesh or stencil calculation, because I've arranged it so that the caching strategies is such that adjacent rows that run off the end of a chunk, the next chunk's likely to be close to the first guy. So if you're walking forwards through their data but looking at your neighbors on either side, or a few sets of neighbors on either side, then you're going to get some duplication of data, but it's going to be in the order of like 3 to 5%, and it's not so much that you care. So you pay the cost one time to haul it in, and then after that it's fast, and there was some duplication. This node had what he was working on plus the neighbor on either side, right? So it's not so much data blow up that you die in it. So here's an example of filtering and counting. So all underage males. And I'm saying another MR task, a map says, oh, I have age and sex, and I ask the question, return a 0, 1, and the reduce is just add them up. And the do all hand it the two vectors in question, and this will go do the right thing and give me all the count of underage males in my data set. So here's one where I want to gather them instead of just count them. And here, the new thing is I have an appendable vec, which is one I can do an append on, and append gives me a variable-sized output. So it's not like A plus B equals C, where I know that the C output is identically sized to the A and the B. Here the output is different. It's smaller, but it's variable-sized. I will guarantee you the order of appends, so it's parallel append across the cluster, but with guaranteed ordering of things.
Yeah, I noticed that in the implementation of map here and on some previous slides, there's apparently you can rely on the fact that all the chunks are the same length.
Yes. So that's part of the data layout. I promise you that all the chunks are the same length.
Okay, I was going to ask you, because of the possibility of missing data, do all vectors naturally have the same chunk organization, or is that something you engineer? And so you do that sort of lining it up ahead of time, or do that on the fly as you run the map? What's going on there?
So I do that ahead of time when I inhale the data, that I arrange. OK, so backing up a step, most of the data is big and sits on disk. Network is 100 times faster than disk. So when I pull it in off the disk, I have a one-shot opportunity to shuffle where you can hardly see it for the disk speed. So I'll do a shuffle after it comes in to do some data layout games. Amongst them will be the chunk layout such that every chunk that's on a given machine has the same count of rows, so I can call map on identically laid out chunk boundaries. Right? So it's not that you're required to only access rows within your chunk. You can step off either side by doing the on any row. But if you access just the rows within your chunks, I guarantee you fast access. Right? When I say fast, I mean it'll boil down to load a byte from a Java array, shift scale add, and then play the math after that.
When you say loading from disk, that's the initial load?
Yeah, initial load. If you end up pulling in more data than you have RAM in your cluster, you will be disk bound now, right? And then you don't care, it's all disk speed. But if you keep it within the set of RAM in your cluster, so for instance, a logistic regression will be 5 to 10 passes over the data set, right? So I pull in 100 gigabytes of data from disk. That's a really big logistic regression these days on anyone else's system. We'll do it in a few seconds because it's all RAM speed. Okay, here's a group by, where I'm just going to count like how many cars people have by the age. And here, the for loop for all your age, and then just do the obvious thing for pulling the age in the car out, and then just bump a thing. So one of the things to notice here is that this car ages plus plus is a side effect. I'm writing to the car ages field, right? And when I write to this, it's single-threaded, privately accessed, because I have said new within the map. And when I say new within the map, this is now an output field. And it's private to this map call. And so I have single-threaded access to the plus plus. I don't drop any counts. I don't have any locking here on the plus plus. But I have to roll it up in a reduce call. So the reduce call is saying, give me a histogram that's to this pointer and give me one on the right-hand side and walk through the array and add the parts together. And the nice thing about fork join is it guarantees me that this is also single-threaded, and it happens pair by pair by pair as I walk through the maps. I'll do this last reduces across the cluster and a log tree roll up across the cluster once you're done within a single node. So here's a distributed hash, count uniques. Starting at the bottom here, I say make me a new uniques object, pass in the set of visitors I want as a vector, and I look at my distributed hash map and I ask its size, and I'm done. Up here, I'm going to say give me a new distributed hash set, and then it's add you in, and that distributed hash set is, the hash set is taking care of the business of removing the duplicates for me. But I set this guy up in the init call, not in the map. So this is usually a read field then. And that I'll make a shallow copy of this on every map call, and you'll have a shared version that everyone's reading from, except this guy's actually concurrent safe, so he can be used as a written thing. But because he's an output field, I still need a reduce step where I have to do a put all to merge hash maps together that came from hash sets that come from different nodes on a cluster. So what really happens here is you get one hash set per node in the per JVM, per node in the cluster. All the maps that running in parallel are poking into it, right? And because it's a non-blocking hash map, it's a concurrent hash map, the duplicates get filtered race safely. And then when you're done, an individual JVM has one of these maps that has the count of uniques it's got locally, and then you have to roll up across the cluster. And so the reduce call picks them from across the cluster and does a put all. Now this guy actually under the hood, I'm hoping the put all will say if the this is equal to the that, then don't bother, it's the same hash map. And you need to add that line of code if put all doesn't do that for me already, but I don't know what the standard JDK put all actually does. Does that make sense? Okay. So the sort of summary here is that most simple Java just works. I've done some more interesting things in inner loops, like a lot more interesting things. We have some pretty complicated math algorithms running around, and I can just write Java code and have it just work. That's the nice thing about it. It's fast, parallel, distributed, read, write, append. Reads are pretty much the same speed as reading from a plain old Java array, because the memory is, the size of the data is much bigger than my cache, so therefore I am stuck by memory bandwidth, so therefore I have plenty of time to do decompression. Writes are a little bit slower because amongst other things I will recompress when you're done writing. So if you write into a vector that the compression scheme doesn't support the size data you wrote, I'll inflate it under the hood, take the writes as a fully generic form as possible, and then recompress behind your back. The conflicting writes will follow the JMM, where synchronization happens between map calls, but not within a map call, within a do-all, across do-alls, but not within a do-all. Or if you ask for it. And if you ask for synchronization requirements, you'll get memory stalls such that the synchronization will happen right. And it could be, the stall could be as far as going to another node in the cluster and coming back. So you'll see some UDP packet transactions running around. Mostly, I don't expect people to write useful code where both people are scribbling into the same data structure at the same time. But there are things where you want to do stuff concurrently, updates concurrently. And so I do have support for transactional updates and a key value. You can take a key and say transactionally do an update on it where we replace it with a new value atomically. And that actually works pretty quickly. Those can be pipelined through the cluster as a one UDP packet from here to there, where I send the code saying run this lambda expression on that node over there, and he'll do an atomic update of the lambda expression on the result for the transaction. And we do that a fair amount for doing all kinds of control logic under the hood. So we're writing big data analytics is what the company's doing in business for. Generalized linear modeling, ADMM style or GLIMNet, logistic regression, Poisson gamma distributions, random forests, gradient boosting, k-means. So these are basically state-of-the-art algorithms. They're running distributed. They're working solidly on the 100 gig data set size scale, and we're trying to upscale. What I found is like every time I add an order of magnitude in the size of the data I handle, it's about 3 months of stability work, performance and stability work to get it to work right. We have just recently got paying customers, so that's really nice. We're about a year in business, and we got paying customers. Is good. And go play with the Git, download and run. Let me know what you think. So I have some other cool stuff that I ran out of time for, or space maybe. I have a reliable UDP system under the hood, integrated with remote procedure call for the obvious reasons. Talked about the lightning talk. TCP is reliably unreliable. The version of H2O like 3 months ago would cause TCP to fail under load 100% of the time. But I had a reliable UDP framework, so I wrapped TCP in it as well, and so the problem went away. I've been playing with fork join for a long time, and so I have a bunch of stuff, like I have priority queues in my fork join land. Distributed fork join. I can survive fork bombs and lost threads, and like the standard fork join, if you throw an exception, the standard behavior is it's silently thrown away, and the thread like either dies or disappears back in a thread pool ready for action. But the work he was doing is lost, and so was any exception. And so I have to catch all exceptions and forward them and do something intelligent. And then I have a key value store that basically uses a hardware-like MESI protocol that lets me have sort of really fast access if you're not actually doing conflicting writes and reads and writes. And even within the conflicting reads and writes, the latency overhead is typically a network packet out and back. It's however fast you can shuffle a UDP packet back and forth. And that's probably it.